Section 6, Part B, Continuous Random Variables. Now, before we go on, let's recap on these rules that we talked about. Rule 4 did have this one little caveat on it, but notwithstanding, these rules are always true. That is to say, they are true for any random variables. They are true for discrete ones, where you can list off the probabilities in chart form. They're true for continuous ones, where you can't do that. We talked a little bit about this. Continuous random variables, you can't list off everything they can be. It's an infinite number of dots. So you have to use area to represent probabilities. So in particular, you've got the mean and standard deviations of random variables x and y. These rules are true. These rules are true if you have just computed the means and standard deviations from charts that you were given. They're true if you've just computed the means and standard deviations of charts, which you have in turn computed. Or they're true if they don't give you the probability distributions of x and y because they don't choose to or because they're too complicated. But nevertheless, they give you the means and standard deviations. In other words, that's the point of these shortcuts, right? All you need is the mean and standard deviation of x and y. You don't need the probability distribution. You didn't need this chart in order to find the mean and standard deviation of r plus b. That was the point of the shortcuts. That's what makes them shortcuts. So people have a way of missing the obvious, but these rules are true whether or not you were given the means and standard deviations of x and y, or whether you just computed them yourself. So bear that in mind as we go on to talk about continuous random variables. A continuous random variable can assume any value in an interval. We talked about a continuous random variable can be any real number in an entire interval. Could be a finite interval or an infinite interval. We'll talk about that. But any dot along the way, basically. Now again, in the real world, few things are perfect. You can't measure things with infinite precision, so we've got some real world limitations going on here, but the principles remain the same. Our infinitely sharp spinner, in as much as we could ever create one, could be any number between 0 and 4, or any other uniform distribution, uniform continuous distribution, that nice rectangle shape. Pick a random real number uniformly. Pick a random real number between end and end in the, quote, obvious way. Well, visualized by our infinitely sharp spinner, right? Straight up, starting point, quarter of the way, half the way, 3/4 of the way, all the way to our end point. 0 to 4 is just a simple example. It could be 5 to 83, right? A quarter of the way, half the way, 3/4 of the way, all the way. So it could be rectangular shaped probability, in which case a continuous random variable, remember, you need to use areas to represent probabilities. If it's rectangular shaped, that's relatively simple. Areas are more rectangles. Or it could be something right skewed. Pick an income of somebody in the United States. Well, remember, you're going to get a pattern that looks something like this. And if you could compute areas left of tick mark, right of tick mark, between tick marks, then you'd be good to go. If could, would. You can't without a lot of calculus. There's not a lot of areas under curves that we're going to be able to do by hand. In section 3, we talked about the uniform ones, the rectangle ones. They're relatively easy. Even something like an isosceles triangle, remember, if you tackled that problem, was something like real work. And the rest of these are all normal distributions, bell-shaped curves, where you can't actually compute those areas, but you can look them up on our charts. So any of our random variables, well, from 3 onward, any of our normal-shaped random variables from a probability perspective, as I said in the last video, are continuous random variables. Pick a pregnancy length. Pick an SAT score. Let X represent the potassium level of a random person or a random reading. Pick a batting average in the 1910s, whatever. Pick an auto engine crankshaft dimension. Pick a cholesterol level. Pick a snow tire lifetime, tread life, whatever. Pick a body temperature, and so forth, and so on, and so on. All of those examples were normal-shaped, continuous random variables, or close enough. You can't measure a tire tread life with infinite precision, but you can get it down to a tiny fraction of a mile, right? Height of a random person in the world, probably normal-shaped as well, and so forth, and so on, and so on. Probabilities of continuous random variables have to be understood in terms of density curves, as we talked about in section 3. Nothing new here, except now rather than talking so much about how much of the whole qualifies, what percentage of people have an SAT score less than whatever, we're instead taking a probability spin on it. What is the probability that the person you pick has an SAT score less than whatever? But as we beat to death from the beginning, the one is exactly what we mean by the other, right? So there's really nothing new here except calling it probability. Other than that, we've done it in section 3. We did the rectangle. I mentioned the triangle in passing. The normal ones, you have to look up the areas. As is always the case, right? The rectangle was an easy example, but it was not an important example. Like I said, it's a jumping on point. Without a lot of calculus, you can't really compute areas under these density curves. We're going to reference them. And the only one we've really done so far is the normal shape. Why that is, we'll see. For instance, the number of heads on 5,000 tosses of a fair coin is approximately normal shaped. Let's see, where was this in the notes? I think it was probably in the review of normal procedures one. No, it was in the how to use probability rules to make charts. Pick 1, 2, 3, 4, 5 people, the number of blue-eyed people you get. Well, pick 80 people, the number of blue-eyed people that you get. Thought of as individual bars is very complicated, but thought of as a smooth curve, very familiar, right? Sometimes things can get so complicated that they become easy again. Yeah, the individual bars are complicated to think about, but you don't have to think about the individual bars. So more on that as we go, but it gives you an idea how important the normal shape in particular is. Pick an example of anything that's normal shaped. Now you've got a continuous random variable, in particular a normal shaped continuous random variable. So there isn't much to say about continuous random variables that we haven't already said. In theory, you use areas to compute probabilities. In practice, there's not a lot of examples we can do in a course like this. We do a lot with the normal shape, but those we look up. Point number 3. Point number 1 was the rules. Point number 2 was some concluding remarks about continuous random variables. Point number 3, like I said, it's a series of miscellany in this section. The rules at the top work for any random variable. I mentioned this at the beginning. The rules at the top work for any random variable regardless of where their means and standard deviations come from, whether you've just computed them or whether you're given them. Notice the way all of these section 3 problems played out, right? You can't be given the pregnancy lengths of everybody there has ever been. If it is true that the length of human pregnancies is got mean 266 and standard deviation 16, then although it is true that by that we mean the average of all possible pregnancies, etc., the one thing you could bank on is that nobody has found the average of all possible pregnancies, right? Clearly, the only way you could ever know that the mean length of all human pregnancies is 266 is to be told it by somebody, right? In other words, the people telling us this are not 100% sure they're facts either. It's guesswork. They're using statistics. More on that later. But this is the kind of thing you would need to be given at the start of the problem, as we typically were, of course, right? When we had a normal-shaped random variable, the first thing they did was tell you its mean and standard deviation. Now, later on in the course, that will get a bit more complicated, but that's where we are at the moment. If you have a continuous random variable, in particular a normal-shaped one, you're typically given the mean and standard deviation at the start of the problem. But wherever the mean and standard deviation of a random variable come from, the rules at the top are still true. They're true whether we've just computed them from the principles in section 5. They're true whether we're given them at the start of the problem. Point number 3. A linear combination of normal-shaped random variables is still normal. Now let's think about this. In general, when you combine repeat performances of a random variable, you get something very different, right? For instance, one roll of the die looks something like this. The sum or average of two rolls of the die looks something like this. The difference between a sum and an average is just a unit change. So whether it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for sum, or divide everybody by 2. You know, a half, 1.5, 2, 2.5, 3, peaking at 3.5, 4, 4.5, 5, 5.5, 6. Again, the difference between an average of two rolls and a sum of two rolls is just dividing by 2. It's a unit change, but the principle remains the same. The pattern remains the same. So one roll, uniform, all bars the same height. Sum or average of two rolls, a very different shape. Let's just stick with sum. So one roll looks like that. Add together two rolls of a fair die, and it looks something like that, only 2 to 12 on the scale, right? The point is that when you combine repeat performances, you get a different probability shape. Now there's two things to say about doing it once versus doing it twice. The more obvious one is that the shape is different. So combining repeat performances of a variable into a single new variable, add two repeats for instance, does warp its shape. The second point is a little less obvious. It is warping its shape in predictable ways. It is pulling the probability back toward the center. This becomes more likely. Over here and over here become less likely. In other words, the probability is shifting inward. And although we'll talk about this in a future section, section 9, that very much continues to be true as we combine more repeat performances. And my only point at the moment is that the shape is contorting, right? Well, if nothing else, there are more bars than there were before, right? So it's definitely not the same shape. And the other example that we talked about in passing was back in section 3, where we had a uniform version of a continuous uniform version of the same principle. One spin of the spinner, rectangular, or square if it's 0 to 1. Average or sum of two spins of the spinner, again, it's just a unit change, divide by 2 or not. Average or sum of two spins of the spinner was triangular shaped. Well, because I told you so. So once again, we see single instance rectangle, put two repeats together, and you get something triangular, which number one is a different shape, but number two, notice that the area is gravitating inward. More on that in future sections. My point at the moment is that when you combine old variables into new ones, in general, you warp the probability shape. Even if it's something as simple as two repeats of the same kind of phenomena, red die, blue die, first roll, second roll, first spin of the spinner, second spin of the spinner, or whether it is or not. X and Y could be totally different things, but when you combine a probability shape with another probability shape by adding the two numbers you get, the new probability shape is generally speaking going to be a different shape. The normal shape, on the other hand, is very exceptional. There's something very stable about the normal shape. Now, as we scroll down a couple of those documents, you can sort of see where we're going with this. But for the moment, let me just say that the normal shape is very stable. Once you have it, you don't tend to lose it. So if you combine in any elementary way, I'll explain, if you combine normal shaped, bell shaped random variables, continuous of course if they're normal shaped, then you get another normal shaped variable. So if x is a normal shaped random variable, then so is multiply by any number. That's just a unit change, right? A bell centering at 3 feet, a bell centering at 36 inches. Multiply everybody by 12, and so forth and so on. Unit changes are not going to change the shape. They're just going to make it fatter or thinner if you superimpose them. So multiplying everybody by a number, if it's normal shaped in the first place, multiply everybody by a number, still normal shaped. Add or subtract a number, well, of course it's still normal shaped. We've already established that adding or subtracting a number is just physically moving it back and forth on the page, right? So if it's bell-shaped here at 10, then adding 3 to everybody, it's bell-shaped here, centering at 13, and so forth and so on. Also, x plus y, if x and y are normal shaped, when you add them, you still get something normal shaped. Well, remember, that wasn't true for the die. 6 bars, all the same. 11 bars, peaking in the middle, pyramid shaped. It wasn't true for the spinner. Rectangular, triangular. But for the normal shape, it is true. If you take two variables that are normal shaped and add them together, that new variable, that new number that you get, his randomness pattern, is also normal shaped. Likewise, subtraction. Or put it all together into one big gulp of a principle. Number times x plus number times y. For instance, if a is 1 and b is 1, we get this. And if a is 1 and b is minus 1, we get the previous. And if a is 1 and b is 0, we get this, and so forth. So this is basically a catch-all for all of the previous. This is what we call a linear combination of two variables. Number times the one plus number times the other. And it covers everything that's preceding, as I just said. So any elementary way of putting normal shaped things together, it is still normal shaped. Why is this important? Well, it's our first hint of what we were talking about earlier on in the course. So far, and that'll continue through the end of this section, whenever something has been normal shaped, it has been so because I have told you so. It's been very dogmatic. Assume for the sake of argument that something has a normal shape. Go from there. That's how all those problems played out in section 3. It's how the following problem is going to play out. Later on in the course, we'll see real-world situations. Later on in the course, we'll see why the normal shape is important. We'll see how it naturally arises. We'll lose the assume for the sake of argument it's normal shaped and see why it's such an important shape. So far, things have only had that shape because I've told you they do. But here's our first hint of where we're going with this. There's something different about the normal shape. For one thing, it's very stable. Once you've got it, you don't lose it. The other thing that's kind of unique about the normal shape was sort of obvious from some of the scrolling down we did in those documents, but more on that in sections 8 and 9. So here's a problem that puts together pretty much everything we've done so far. Remember, we're approaching the end of section 6, which is the end of our background information part of the course. Starting in section 7 and continuing through 9, we move into the theory of statistics part of the course. So we're approaching the end of our background information. So what I want to do is I want to give you an example of a problem which will put together, if not everything, then a great deal of what we've talked about in the preceding sections. Here goes. Suppose Sam and Jack are playing golf. From past experience, we know that Sam's golf scores vary normally with mean 110 and standard deviation 10. Recall from the previous sections what that means. It means if we could make a histogram of all his golf scores, parse that however you want. All the games he's ever played, all the games he ever could play, an ideal of his playing experience, if you like. Then number 1, the histogram would be normal shaped. It would have that bell shape. If we could find the mean of all possible golf scores, or all scores he's ever had, it would be 110, data, x bar, if could would. If could would, if we could find the data s standard deviation of all golf games, again, parse all golf games however you like, it would be 10. And all the things that that implies. This would be this 110 would be the center of the bell, 10 would be the spread of the bell in that inflection point sense that we talked about, all the different ways that that statement comes together as we talked about in section 3. Sam's golf scores vary normally with mean 110 and standard deviation 10. Jack's golf scores also vary normally with mean 100 and standard deviation 8. Let's think about that. Now remember, the low score wins in golf, so Jack tends to be the better player. And as you might have expected of the better player, his scores vary less than Sam's. So number one, he is the better player in the sense that on average he gets a lower score. And he is more consistent in his games. His games don't vary from one to the other so much, as you would expect of a better player. But theoretically, the one need not have anything to do with the other. Find the probability that Sam wins. So Sam and Jack are playing golf. Sam's golf scores vary normally with mean 110 and standard deviation 10. Jack's golf scores vary normally with mean 100 and standard deviation 8. So, what is the probability that Sam wins? Well, let's get a feel for that, okay? First, real world distractions here. Let's get a feel for this question. What is the probability that Sam wins? Now remember, Jack tends to be the better player in the sense that on average he gets a lower score. So if you had to bet, it would not be on Sam. The probability that Sam wins, it is the easiest thing in the world. If you've done any practice with these normal charts, and you probably should have, then you know that it is the easiest thing in the world to lose a sign, look at the wrong side of the chart. You always want to ask yourself what's plausible. You're not going to bet on Sam. Sam tends to be the worst player. So the probability that Sam wins logically should be under a half, right? It is technically unlikely that the worst player will win. So our answer should be less than a half. But how unlikely is it? Well, remember, we've got the 68, 95, 99.7 rule. We haven't talked too much about it, but loosely speaking, it's not that unusual to be one standard deviation away from the mean, right? 110, give or take 10, that is a relatively typical place for Sam to be. 100, give or take 8, that's a relatively typical place for Jack to be, right? So 110 minus 10 is not that unusual for Sam. It's within the realm of possibility. And 100 plus 8 is not that unusual for Jack, right? So these two bells, one centered at 110, one centered at 100, spreading out as they do, they overlap considerably. I don't have a great picture of that, but something like that. There is a considerable amount of overlap in those bells. If Sam has a good day and gets a score of, say, 100, that is not an unusual day for Sam. It's just a good one. And if Jack has a bad but somewhat typical day and gets a score of 108, well, then Sam's got the better score with room to spare. So there is considerable overlap there. A score of 110 minus 10 is not that unusual for Sam. It's just a typical bad day, a typical good day. And a score of 100 plus 8 wouldn't be that unusual for Jack. It would be a somewhat typical bad day. So with room to spare, 100 is less than 108, and Sam could win. So in other words, it's going to be less than a half, but it's not going to be cosmically less than a half. It's not going to be 1/10,000th. It's going to be within the realm of possibility. Wild guess, somewhere between 20 and 30%, 10 and 40. Not really unusual, but less than a half. Wild guess, 20, 30, 40% chance. Wild, wild guess. But we don't need to guess. We can check it out. Point is, we've got an idea of what's a plausible answer. So first, let's quantify. Let S represent the random variable that represents what the score Sam will get today, and let J represent the random variable that represents what Jack will get today. Well then, probability being what it is, this is how all possible games play out, or they're the probability rules for what S is likely to be the next time. These are the probability rules for how all Jack's possible games play out, or they're the probability rules for Jack's next game. The one is exactly what we mean by the other, remember. So S is the score Sam is going to get, J is the score Jack is going to get, and those are the probability rules for them. Now remember, if we wanted to say what's the probability that Sam gets a score less than whatever, then we would subtract 110 and divide by 10 and go to Z and use the chart and so forth. But let's be more interesting. What does it mean for Sam to win? Again, low score wins in golf. So Sam winning mathematically is the number that S happens to be, Sam's score on the next game being less than Jack's score on the next game. How do we compare variables? Well, we don't. We combine them into a single variable and compare it to a number. Let's subtract J from both sides, or just hit it with logic. If J is the bigger one, then S minus J is negative. So subtract J from both sides. S minus J is less than J minus J. So there we go. We want S minus J being less than 0. So let's put it all together. Number one, if S is normal shaped and J is normal shaped, then S minus J is normal shaped. That was point 3. When you add or subtract normal shaped things, you get another normal shaped thing. A typical add problem would be time to do one thing, time to do another, time to do both. This is a typical subtract problem. You're looking at the one being less than the other, the difference being something. So S minus J is normal because S and J are both normal. Which means what? Which means that this normal creature can be compared to this number. Because it's normal shaped, creature S minus J can be compared to number 0 by subtract its mean, divide by its standard deviation, Z-chart, look it up, done. So we need the mean and standard deviation of this creature, and that's where our rules come in. The mean of S minus J can be found from the mean of S and the mean of J. Now again, remember, we don't need to know the actual chart form of S and J. There isn't one. It's a perfectly smooth bell. Well, I mean, golf scores are probably in whole numbers, so a little jaggedy perhaps. But we don't need to work it out from a chart in column, column, column form. Like I said, it's enough to know the mean and standard deviation of S and J. It's enough to know the means of S and J, and then we can find the mean of S minus J. Again, means work in the obvious way. If you subtract two variables, then you subtract their means, right? The mean of S minus J is the mean of S minus the mean of J. Now bear in mind there's no particular reason that has to be positive, so watch the sign. If you make a sign mistake, bear in mind that you're not betting on Sam. Our answer should be less than a half. Like I said, check it against common sense. It's easy to lose a sign, but in point of fact it's positive 10 in our case. Now if you are subtracting a negative, we're not, but if you are subtracting a negative, be very, very careful, of course. Minus minus is plus. But in the right order, it's the mean of S minus the mean of S minus the mean of J, which happens to be positive 10. As for the standard deviation, remember you can't add or subtract standard deviations. The one is 10, the other is 8. It's not going to be 18, it's not going to be 10 minus 8 or 8 minus 10. You square them, add them, take the square root. 10 squared plus 8 squared square rooted. Notice that not only is it not 18, it's less than 18. It's less than what you would get by adding them. Subtract not even being in the game, of course. You add them. Whether you add or subtract variables, you square add and take the square root of the standard deviation of the what you got. Now remember, minus becomes plus, just to beat it to death. So this is the mean of S minus J. This is the standard deviation of S minus J. Remember, to use our Section 3 normal chart procedures on a variable, we need to know three things. We need to know that it's normal shaped, done, point Roman numeral 3 above. We need to know what to subtract, and we need to know what to divide by. So we're good to go. Now, bear in mind, for this formula, the mean is okay, but for this formula to work, S and J have to be independent. Are S and J independent? Is it the case that whether or not Sam is having a good day or a bad day, however Sam happens to play today, it's not going to affect Jack's score and vice versa? No, we're talking about human beings here, but that's easily fixed. We'll blindfold Sam, send Jack through the course, blindfold Jack, send Sam through the course, so that neither one of them has any idea how the other is performing today. Now we're good. So that's easily solved. We can assume, for the sake of argument, that however Sam happens to do today has no bearing on how Jack happens to do today. S and J are independent. Why not? So yes, we can use this principle. So we're good to go. S minus J is normal shaped because the pieces are, and we've used the rules to find its mean and its standard deviation. Therefore, it can be compared to any number you like. Now, the fact that this number happens to be 0 sometimes confuses people, but that's just a nice problem, remember. What's the probability that Sam wins by 5 points? Well, that you've got to think about. You know there's a 5 involved, but you're not sure what side it's on. So grammatically, this is just the simplest question to ask. For the most part, we'll stick to that. There is an example, I think, of one where you've got a number other than 0 here, but it's one of the harder ones in the practice problems. So S minus J is less than 0. S minus J, because of what's directly above, we've quantified its rules of randomness. Bell-shaped, mean, standard deviation. Therefore, it can be compared to this number. Again, the fact that this number is 0, don't let it confuse you. We'll subtract the mean, divide by the standard deviation, and that'll turn it into Z. And we get negative 10 divided by, well, answer key, right? 10 squared plus 8 squared is the square root of 164, and the square root of 164 is on my calculator screen. Answer, well, let's do it this way. Parenthesis, answer, minus 10, actually the other way around, negative 10, 0 minus 10 divided by answer is negative 0.78086888094 something. For our purposes, all I want to do is make sure that it really is this to 2 places after the decimal, right? And it is. So now we're good to go. Negative 0.78. Negative 0.7 row, 8 column, 2177. More or less what I was expecting. It's not cosmically unusual like 0006. It's not more than half. It's plausible. 2177. So there you go. The probability that Sam will win the next match, 0.2177. About a 22% chance that the worst player will win next time. Depending on your answer, depending on your point of view, it's either unlikely that he's going to win next time, or he will win 22% of the time they play. It checks our intuition. Less than a half, but reasonably possible. So there's an example of how all these come together. An add problem would be more or less the same principle. There's a lot of those in the practice problems. Time to do one thing, time to do another, time to do both. Amount of one thing, amount of the other, amount of both. Weight of one, weight of the other, weight of both. There's a lot of assembly line type problems there. Or you can do a subtract where you're comparing two people's scores or some such. So the add problems work out exactly the same way. In fact, the hard part is exactly the same. The standard deviation of S plus J is still 12.806. But if you're adding variables, of course, here you would get 210. That's the only major difference. If they're playing together, right, you want to know their combined score and what it's likely to be, for instance. Let's see, what else? Various miscellany. Let's go back to this formula here. Why is it that this number is less than you would get if you added them? And apart from our sarcastic little heads and tails example, more than nothing. Well, this is easier to do in class, waving my hands around, but I'm going to make a try at it. It goes something like this. Let's say that x and y were completely and utterly dependent on one another, that whatever x happened to be, y happened to be. Take two dice, for instance. If the red die happens to land at a high number, then the blue die lands at a high number. If the red die happens to land at a low number, then the blue die happens to land at a low number. Or you can tackle this from a semi-sarcastic perspective, if you like. Let x be the number on the die, let y be the exact same number on the die, right? So that you're literally using x and y to mean the same thing. First die land, x is 1, y is 1. X is 6, y is 6. X is 2, y is 2. X is 5, y is 5, and so on and so on. What if they moved the exact same way at all times? Low end, high end, toward the middle, and so on and so on. If that were the scenario you have, then it would be like adding their standard deviations. Now let's tackle it from the other point. It's not vitally important. Know that. I'm just illustrating a principle. Let's tackle it from the other end. What if x and y always perfectly counterbalanced one another, so that if x was on the high end, y was on the low end? Let's take dice. If x is 6, y is 1. If x is 3, y is 4. If x is 5, y is 2, and so on, so that they're always moving to exact opposite extremes. If x is as high as it can get, then y is as low as it can get. If x is just a little higher than the center, then y is just a little lower than the center, and so on. What if they always perfectly counterbalanced each other out? Well, we saw an example of one of those, and it was this, right? Number of heads, number of tails. They always move in opposite directions. H, 0, 1, 2, 3. T, 0, 0, 1, 2, 3, so that they're always moving in opposite directions. 0 and 3, 2 and 1, 3 and 0, 1 and 2, and so on and so on. And we see what happens. They always add up to the same thing, and there's no variation whatsoever. They always perfectly counterbalance one another so that the standard deviation is nothing. Now the reality, of course, because they're independent, because they have nothing to do with one another, the reality is somewhere in between, right? Some of the time, because the red die and the blue die have nothing to do with one another, sometimes they're going to move the same way. Red die happens to be high, blue die happens to be high. Sometimes they're going to move in opposite ways, right? Red die is a little less than the center, blue die is higher than the center, and so forth and so on. Sometimes they're going to move in the same way, high, high, low, low, center, center. Sometimes they're going to move in opposite ways, high, low, high, high, low, center. Therefore, the reality is that it's going to be more than nothing and less than you would get by adding them. So everything about the formula makes sense. Now, if you think of x and y like we did with the first roll, second roll, to be repeat performances, which is really where we're going with this. First spin of the spinner, second spin of the spinner. Height of the first person you measure, height of the second person you measure. First roll of the die, second roll of the die, and so on and so on. We can combine even more of these, as we'll see. If you think about repeat performances, then what we're saying is that when you combine repeat performances into a single variable, it doesn't vary quite as much as you might expect it to. So that ultimately where we're going with this, and we'll talk about this more in the middle half of the course, starting in the next section actually. Ultimately where we're going with this is that larger samples tend to be more predictable and more stable. When you combine many repeat performances into a single variable, the result is it doesn't vary as much as you would expect. It tends to be more predictable. Hence, as we saw in a previous section, or at least these are notes from the future, but, well, actually not. This was in section 5, right? So that if you're talking about what happens when you do 2 or 3 repeats, pick somebody who may or may not have blue eyes, pick another, things tend to be on the jaggedy side. They're unpredictable. You might be one bar, you might be another. But when you're talking about putting 80 repeats together into a single number, then things tend to be very predictable. I mean, sure, thought of as individual bars, it's a bit of a mess. But thought of as a shape, it's very predictable. We've got a very good idea what's going to happen. Tackle it from another point of view. If you flip a fair coin 5 times, you might get 0 heads or 1 head or 2 heads or 3 heads or 4 heads or 5 heads. If you flip a fair coin 5,000 times, then you've got a pretty good idea what's going to happen. You're going to get about 2,500 heads. Now, about 2,500 covers a lot of ground, and we'll worry about that later. But you've got a pretty good idea where you're going to land. So when you combine many repeat performances into a single variable, the result tends to be very stable. This principle is the driving principle of statistics. It basically says in so many words that the more independent repeat performances you combine into a single variable, the more stable and predictable everything gets. It's the principle that makes everything in statistics work. How this plays out, we'll see mathematically, and we'll see from a practical point of view starting in the next few sections. This gets us through section 6. This gets us through the background information for the course. In sections 7, 8, and 9, we'll talk about the theory of statistics. I'll do it in an overview kind of fashion in section 7, devoid of any real math. And then in sections 8 and 9, I will supply the math. I'll supply mathematical detail to what I said in section 7. So that's just where we're going. Section 7 will be an overview of how statistics works in more wordy than mathy terms. And in sections 8 and 9, for different types of statistics, we'll supply the mathematical detail. But by now you've got an idea of where we're going with all this. Everything in statistics is based on probability. So what is the takeaway from the first few sections as we wrap up this part of the course? Section 1, numbers have shapes. Sets of numbers have shapes. Section 2, there's some things we can compute from a set of numbers that are descriptive. Section 3, how to use the normal charts. Section 4, basics of how probability work. Section 5, the idea that randomness always has a shape. Randomness always has a shape. It's not enough to say that something is random. You've got to quantify what you mean by that. You've got to talk about its probability distribution. You've got to talk about the shape of its randomness. And section 6 is kind of where we're pulling it all together. So we'll start next time talking about what a statistic is. Better late than never. And that'll be that. We're now through section 6.